So we're going to wrap up our overview of Java synchronizers with this lesson, giving a brief discussion about so-called usage considerations. And as we'll see, there's a bunch of trade-offs, as is always the case with every type of software. There's pros and cons, there's good things and things that could be improved. And a lot of the trade-offs you'll see here are between performance and productivity, which is often a trade-off in computer software. So what does this mean? Performance really means how fast things run, and productivity means how quickly humans can be efficient in what they're trying to do. And as you might expect, sometimes the faster things run, the more complicated they are to program. So humans' productivity may go down, and then vice versa. Sometimes when we have higher level abstractions, productivity goes up, but performance may suffer. So there's very rarely such a thing as a free lunch where you get everything at the same time. To quote Oprah Winfrey, you can have it all, you just can't always have it all at once. So that's kind of the message we're saying here. Some synchronizers or methods that are part of synchronizers have more overhead, which means that they will make performance somewhat less. And again, usually it's because there's a trade-off in terms of simplicity or productivity with performance. So let's take a look at a couple of different types of locks that will help you navigate through this design space. So one type of lock, which you're actually going to get some experience with in programming assignment 1B, is something called a spin lock. And a spin lock is a lock that causes a thread that's trying to acquire it to simply spin in a loop while repeatedly checking if the lock is available. So it's sort of neurotic. It's like someone who neurotically calls somebody or neurotically sends email or neurotically checks something over and over and over again just to see, they want to know as soon as they get a response. And that's what's called a spin lock. And again, you'll get some experience with that. As we'll see, spin locks typically get the answer as quickly as it becomes available, or they get the lock as soon as it becomes available, but it can also burn CPU cycles unnecessarily, because if the resource is not free for a long time, it'll just sit there and spin. An alternative to a spin lock is called a sleep lock. And that's a lock that blocks and doesn't return to the calling thread, or the calling thread is put to sleep, if you will, until another thread has issued a notification that some event may have occurred that may change the conditions so that the lock that's sleeping can wake up and then make forward progress. And so you'll see that this concept of sleeping or waiting or blocking is another style of lock. And I should hasten to mention that some lock synchronizers, some synchronizer mechanisms will support both spinning and sleeping within the same abstraction by just having different methods. For example, you'll see in some of the methods we're going to focus on, there's something called a try lock, which is used for spinning. And then there's a lock method, which in our case spins, but in other cases, as we'll see later, could go to sleep. And then the third type of lock, which is really kind of a variant of the first two, is called an adaptive lock or a hybrid lock. And that's a lock that will spin when trying to access a resource locked by a thread that's currently running. But if that thread goes to sleep while still holding or owning the lock, then the thread will be put to sleep, because there's no point in spinning when the owner of a lock is not running, because of course that lock is not going to change its state because the other lock that owns it is asleep. So those are sometimes called adaptive locks, which will spin a bit and then sleep if there's no chance of making any progress until they get a chance to make progress again. Some synchronizers are also harder to program correctly than others. And you'll see, once again, there's trade-offs between performance and productivity. So just as a simple example, there's a style of lock called a non-reentrant lock. And a non-reentrant lock simply means that if a thread currently owns the lock and it tries to reacquire it, it will deadlock on itself because it's non-reentrant. In contrast, there's something called reentrant locks, where reentrant locks would simply increment a counter if they currently own the lock and they try to reacquire it. And so people who are taking the course for graduate credit get to implement a reentrant lock for assignment 1B, whereas students who are taking the course for undergraduate credit get to implement a non-reentrant lock. It's just a little bit simpler. And the thing to remember is reentrant locks are somewhat easier to program because you don't have to worry about self-deadlock, but they're also a bit more expensive. And so you have to be wary of that. So once again, there are these trade-offs that come with performance versus productivity. Now, there's also other ways of looking at synchronizers. There's Java synchronizers, which are, as we'll see, implemented as Java classes as part of the Java class library. And then there's also these other kinds of locks that are called the Java built-in monitor objects. And it's very important to understand the difference between these two categories of mechanisms. So the Java synchronizers are, as the name implies, largely written in Java rather than C and C++. Although there are some low-level mechanisms or low-level methods that are written in C and C++, which are then accessed using some form of the Java native interface, which is a really cool technique that allows developers of abstractions like synchronizer classes to implement some of the methods with low-level techniques, but give a Java interface to programmers who are using their abstraction or using their class. So we'll talk about this a little bit later. We'll talk about things like compare and swap methods, which are really low-level operations provided by the underlying Java execution environment and operating system and hardware and so on, and other methods that, again, that are very low-level called park and unpark and so on. But the key point is that Java synchronizers are exposed using Java, and they're largely written in Java. They also provide many features and have very powerful semantics. So as opposed to the Java built-in monitor objects, which are written in C++ and C, they are more efficient in some ways, but they're also more limited because they don't offer as wide a range of features. And a very simple example of this would be the synchronized methods and synchronized statements that you get with Java built-in monitor objects. We've looked at a couple examples so far where you put the synchronized keyword in front of a method or the synchronized keyword in front of a block of code or a statement sequence. And those synchronized methods and statements are very, very efficient, but they're also very limited in what they can do. They can basically acquire the lock, locking if it's not available, and unlock the lock. Whereas the Java synchronizers like NonReentrant Lock, for example, or stamped lock, have many, many more features that do a wider variety of things and are much more powerful, although there's a bit more overhead to some extent. Again, that trade-off between performance and productivity we keep talking about. So that's the end of the overview of the usage considerations for Java synchronizers. This is just meant to be a high-level kind of preview of coming attractions as we go through the various synchronizers, as we go through things like NonReentrant Lock and stamped lock and semaphore and condition object and Java built-in monitor object locking mechanisms. We'll go through their usage considerations in much more detail. So by the time you're done with the course, you'll not only understand the big picture view, which is what I'm giving you now, but you'll also have a very good understanding of the details, both conceptually from the lectures, as well as getting some hands-on exposure to how to program them in practice through the assignments.